Welcome to lecture 20. So we will discuss the features and as well as the utility of both Unix and Windows as a real-time operating system. So we have discussed both monolithic and microkernel based operating systems in the previous lecture. So what we have discussed is that we have an underlying hardware layer. On top of that, we have a kernel mode. So in the kernel mode, we have the traditional features of process management, memory management, device management, storage management, and IO management. And on top of the storage and device part, we have the file system. And then we have a system services interface for system calls. And at the very top, we have the application programs. So pretty much Linux and Unix fall into this paradigm. The monolithic kernel, so we have seen this diagram in lecture 19. Everything starting from the hardware abstraction layer to the key kernel modules are all a part of the same whole, right? It's the same program. It cannot be split. So of course, Linux has the notion of loadable kernel modules (LKMs). So LKMs can be used to augment its functionality or modify its functionality at runtime. But that is again not the core of Linux, right? So that is not really a very essential feature. So monolithic OS, the strong points is it provides a single program and address space, Unix, Linux. So these approaches are well understood. The performance is good. It's easy to debug. But of course, the key problem is that the kernel components are not protected or isolated from each other, right? So there is this traditional protection or this isolation is not there. Furthermore, these are not easily extended, modified, or customized, right? It's not really possible to implement a very diverse set of applications on such kind of a monolithic OS or a monolithic kernel. So the monolithic structure that we are looking at basically has a main kernel core that provides a bunch of OS services and a bunch of utility functions that use those OS services to provide services to real applications. So again, the pros, as we have said, is that the kernel is the OS. It is one whole thing, easy to write, debug, and verify. Protection is an issue. And given the fact that we have a large and generic base, which can contain all the device drivers and so on, it's a great idea for a company such as Apple, which also makes its own hardware. So, for example, on an Apple machine, the hardware is made by Apple, right? So it's not made by anybody else. So there is no reason for the Apple operating system, iOS, to actually cater to all kinds of hardware. That's not required because the hardware on which it will run is fixed. So that can be a monolithic kernel because the point is that that much of runtime flexibility is something that we don't require, as opposed to something like Windows, which is actually meant to run on a large variety of machines. So the monolithic kernel has its disadvantages, which is a large kernel size, because all the features have to be compiled, have to be linked and bound together as one kernel, and that kernel would be running. So the size is large. There is a shared address space in the sense that correcting kernel bugs is difficult, and also it is hard to isolate components from each other. So either because of a genuine bug, or because of a virus, or because of an inadvertent issue where one part corrupts the memory of some other part. Uh, Isolating this is difficult. So again, monolithic kernels are well understood in the sense the number of behaviors is kind of limited. So in a sense, it's easy to verify. But in another sense, correcting a kernel bug is difficult because it's still one large code base. The separation is not there. So this can lead to some instability, right? And also for many such designs, particularly for commercial Unix, the kernel code is not available. So it's only the kernel writers who can do it. So if you need any additional feature, you'll have to go back to the authors of the kernel and they need to recompile the kernel, give a new kernel to you. Even though Linux still being a monolithic kernel, it is open source, so it does not have this particular issue. Also, the thing is that given the fact that we are not having the kind of flexibility we may have if we are allowed to dynamically at runtime modify parts of the kernel, is that it is bound to specific hardware and it is bound to specific application needs, right? So, which is fine if, let's say, the scope of usage is limited. But in general, when we are looking at creating any kind of operating system which will be generic means run on a lot of hardware. A monolithic kernel is not a good idea. But as I said, in real time systems, if the embedded system, etc., is fixed, then at that point, a monolithic kernel is okay, right? It all depends upon our application need and the application scenario. So the microkernel, on the other hand, is a minimalist approach where you run as much as possible in user space. The kernel itself is modular and quite small, could be as low as 10 kilobytes, its size, to a few hundred kilobytes. Is easier to port the kernel, easier to maintain and extend. There is no agreement on what should be or should not be there in the kernel, even though the key idea is the critical features such as interrupt handlers, some basic memory management and process handling should be there in the kernel. But as much as possible, it should be sent to the user space. So, as I said, basic process and memory management is what goes. So, then at least the basic idea of supporting different address spaces and memory protection goes in the kernel. Again, the basic implementation of processes and threads also goes remains in the kernel, and basic IPC, inter process communication. So the real goal of microkernel is that make it small, make it flexible, right? So the real goals would be small and flexible. This is fine, right? But it is not simple to make it small. That is the main issue. That to make it small is not simple at all, because this fundamentally changes the way in which we create and deliver OS functionality, where modularity is the key, but size is just a side effect. So we cannot call an OS microkernel based just because it is small, but again, it needs to show the flexibility features that we have been talking about. So the microkernel, again, we have seen this diagram in the previous lecture, where we have a small tiny kernel which is in user mode, sorry, which is in kernel mode, and most of the key features. So again, we have a proto implementation of the process manager, but most of the process manager and scheduler can be again in what's called user mode or user land. Similarly, we'll have a proto implementation of a file system, but most of the file system implementation can again be in user space. And the same holds for drivers as well. So again, it's like a kernel for a kernel. This is what runs in protected mode, and the rest, as much as possible, is sent to the application mode. So for any kind of a client server kind of OS, the kernel would still need to implement scheduling, memory management, and IPC, and but all the other services, and including practical or runnable or advanced versions of these, they can all run in user space. For example, the kernel can say that it will provide a very basic FIFO or round robin scheduling service. But again, it will not be averse to the idea of the user writing a dedicated scheduler and linking it with the kernel. So then what can happen is that when the kernel needs a scheduling service, it can call the user mode process to actually do the scheduling. And definitely other smaller services, for example, setting timers and alarms and all these things, implementing other IPC mechanisms like pipes and message queues, etc., could all go into user space, right? So that is the key idea, that we have our hardware, we have our microkernel, provides very basic services, mind you, and then all the client applications and all the other what should be kernel applications but now run in user mode, they all run in user mode. The client can talk to them and the kernel can also talk to them. So the pros of a microkernel based approach is it's a smaller kernel which is suitable for embedded applications, mainly because of its small size. I'm not saying that embedded applications need a very high level or a very high degree of flexibility. But again, because of the small size, this microkernel based approach is quite suitable. Also, it is modular, extensible, and customizable. So, this again is not something that we would ideally like to do in an embedded environment. This is more for laptops and desktops. But again, in an embedded environment, who knows if we have a lot of sensors and those sensors are specialized interfaces which has not been coded into the kernel, or they have specialized requirements, then again it's a good idea. Also, the other thing is if we have real time requirements and we find the kernel to be coming in the way, again we can go for a microkernel based design where it will be possible for a user process which has a high real time requirement to execute in the place of kernel processes. So, as such, a school of thought does argue that a microkernel based approach makes OS development simpler because it distributes the design and you have well defined interfaces between components. But as I have argued in the previous lecture, this point is somewhat debatable, right? So, one camp may say that a monolithic kernel is better, the other camp may say that a microkernel is better. And of course, for operating system services, no doubt more than one implementation is possible. So, a lot of flexibility is given over here. The microkernel is stable in the sense that it can have fewer bugs, mainly because of isolation, because of component wise testing. But again, as I have said, this is an ongoing debate because someone can always say that, look, you have a lot of components. At the time of creation or at the time of compilation, you don't really know how these components will interact with each other. Given the fact that you do not know that, it would be unwise or impractical to say that the entire thing is stable because it is possible there may be some feature here which will break when this component is run, right? But at least one thing is there is some degree of recovery in the sense if this component fails, we can restart it. Coming to context switches, if I were to compare the difference between a monolithic kernel and a microkernel, so then in a monolithic kernel, we clearly have multiple address spaces in the sense if there is a context switch, well, we go to the kernel, we store the data, we store the context, and we come back to maybe the same user process or a different user process. In the case of a microkernel, what happens is, well, the system call does take you to the kernel, all right, but the kernel itself may now invoke some other code which is actually running in the user space. So the time it takes to actually process a system call will increase because previously everything was within the kernel, but now the kernel would call a program in the user space. That would compute something. Again, it will send the response back to the kernel, and the kernel will send the response back to the user space. So, as you can see, we are paying a price for this flexibility. Again, some cons of microkernel, we could have poor performance as you just saw because number one, given that each kernel call achieves less, we could have more system calls, or if we still keep the same system call interface, you can definitely see over here we have more context switches, right? So each system call has to switch to the kernel can again switch to a user level process, switch back and switch back. So the context switches indeed become more expensive. So flexibility is not a one-way street, right? So there are no free lunches in this world, and definitely OS flexibility falls in that. All right. And every context switch, it does involve a fair amount of work. We have to store some state, we have to restore some state, we have to flush the TLB and restore. So clearly for flexibility, OS services do become expensive. A single system call, as you have seen, requires two function calls and two mode switches, as you just saw in the previous diagram. For real-time applications, however, where the main aim is a quick turnaround time, quick interrupt handling, in a sense there is an interrupt, so we don't do much, we do a little bit, the rest basically runs in user space, which can be scheduled later, right? And and the priority of basically the deferred mechanism. So this is known as deferred processing. So typically in many systems, what we do is we have a top half and a bottom half. The top half is the one that does quick interrupt processing. So this of course is done in the kernel, but most of the bulk of the work is done by the bottom half. And the bottom half, if that is running in user space, it has a reduced priority. So if that has a reduced priority, then at least real-time processes can run. Regarding IPC services, so basically IPC does govern the performance of the OS more so in a microkernel because that is heavily dependent on inter-process communication, right? So if we will have many of these nodes, there will be communication between them, and because of the heavy dependence between them, there will be there will be a strong correlation with the performance of IPC, right? So even though a microkernel itself is roughly comparable to a real-time executive, because we have reduced the overhead significantly, but because of multiple context switches and the high overhead of inter-process communication, things can get worse, in the sense performance can get worse, because we are just not looking at the microkernel, we are looking at the entire flow of getting some job done that will require many rounds of communication between the different entities we have created, both in the kernel space and user space. In the sense, a single call may like take you from user kernel, right, to back. And along with that, you may have multiple user level communication messages. So this will increase the overhead somewhat substantially. So this brings us to the end of lecture 20. So we will continue discussing similar topics in lecture 21 as well, which will be the next lecture.